Welcome to this Cryo-EM course. Last class we discussed about how electromagnetic lens is helping us to converge the electron beam, and it is converging the electron beam as well as it is diverging the electron beam, and that is basically we have a fixed lens system which we are using different kind of magnetic field and which is helping us to converge and diverge the beam at different angle, and that is the time where when we are converging we can use different kind of magnetic field, and then crossover point will move around. So that is we are going to discuss today more, that how that condenser lens 1 and condenser lens 2 system together with aperture is helping us to to image biological sample even using a 300 kV microscope. Also we started discussing about the different types of aberration, and those aberrations are spherical aberration, chromatic aberration, astigmatism, coma aberration, distortion, and curvature of the field. So last class I only discussed about that chromatic aberration, how this chromatic aberration is happening, especially for light microscope. In light microscope I already discussed about that. Okay, so there is a wavelength from 450 nanometer to 750 nanometer, and due to differences in the materials of the lens system, the light rays will be separated, the blue, green and red, and we can see all these blue, green, red line when you will try to image. So sometimes those images will be either when you will collect that image we can see some reddish appearance or greenish appearance like this. So this is the aberration. Now I asked one more question, that okay, this kind of aberration is available in light microscope or any kind of camera we are using. So there is a proper procedure to correct those things. Now the question it is coming, is this possible in electron microscope? In electron microscope, whenever we are using electron microscope, mainly in electron microscope we are using a wavelength in a picometer range, that we already discussed, and we already calculated that wavelength of electron is a picometer range. And can you see chromatic aberration when we are using electron microscope? If we think properly, in last class also I told that okay, so what is that chromatic aberration? There is a wavelength difference, because in visible light whenever we are talking about, there is a wide range. It is coming almost 450 to 750 nanometer range, and within that range there are many different types of light, that is blue, green, yellow, red, everything is merged together. But if we can separate them somehow, it will be reflect in your image. So it is chromatic aberration mainly depending on your wavelength of the light, right? So same thing for electron microscopes also, because last class I started discussing about that chromatic aberration and then we stopped. So today we will discuss more about that. Okay, what kind of differences we can see it here. So if we go here, if we so last class when I was discussing that, okay, what is happening when we have a electron gun? We have a electron gun, and electron gun has a very sharp tip, and we are expecting all the electrons are coming out from this gun, and there is some kind of bias which is helping us to bring the electron down, and then they are converged in one particular point here. And then whenever we are talking about this everything is converging in one particular point, and we are expecting all the incoming electron, whatever electron it is, it has the same energy. So if it has the same energy E, so everything will merge in one particular point and it will be uniform, there will be no difference. But if there is a energy difference, it is going to affect their wavelength also, right? And we are always considering that when we have a electromagnetic lens system, and in particular situation that okay, when there is an electron beam, we are just using ray diagram and we are considering that all the rays are converging in one particular point, and in one particular point or time we are using a same magnetic field. So in the same magnetic field, if you just consider that okay, for objective lens, that is I told you that it is around 2 Tesla. We are using this magnetic field. So you are using an objective lens and you consider that it is a fixed magnetic field we are using, and this is a 2 Tesla, and we are not changing this magnetic field of this electromagnetic lens for a particular time. So we are expecting that all the electron will come here and converge in one particular point. So if the energy of the electron is fixed, the lambda it will be fixed, and we are expecting if magnetic field is fixed, then all the electron will come and converge in one particular point. So there will be no such kind of differences like that chromatic aberration. But when electron is coming out from this filament tip, it is bit difficult to understand that all the electrons are coming at same speed, same energy and same wavelength. There will be some kind of variation, right? So if the electron's energy is different, in one case if it is E, and the other case if it is coming like delta E, or if it is coming like plus delta E. So they are very close to each other, but they are not having the same blink. There will be some kind of changes, right? But here our magnetic field is completely same. There is no change anywhere. And also if there is a no change of the electron, then what will happen that okay, so when they are going to merge here because of this electromagnetic field, because this electromagnetic field is fixed, that is we are using, just consider that we are using 2 Tesla continuously. Now some electron has an energy, that is if I just consider that is E. Now I have some electron has a less energy, but the magnetic field is same. Then what will happen? They will converge somewhere up. Okay, and then they will just follow this one. So you can see there is a similar kind of appearance when we are talking about the glass lens system. In glass lens system, if we just look at what we can see, there is a parallel rays are coming. And if this is an optical axis, some rays it will come like, here there is a red rays. So due to this, quality of the lens, some rays will has a different wavelength, that is red, and then your green rays, it has a different wavelength, that will converge in somewhere here, and then blue it will convert somewhere here. Now what is happening? You can see the separate blue, separate green and separate red. Here also you cannot see that reddish appearance or greenish appearance or bluish appearance, but here you have some kind of, due to the energy difference, some kind of changes in the magnetic field. In one case you can see that okay, lines are converged somewhere here. So the similar pattern we can observe in this particular case also. Now if we want to draw it in properly, so what we can see, we can get it like that. So if someone is asking that okay, do we have this chromatic aberration problem in electron microscope? Definitely we have chromatic aberration problem, and this chromatic aberration, how we will draw and explain these things, that okay, this is the sample. if this is our sample, rays will come out from here, and then we are considering that okay, this is my optical axis. This is my optical axis. In one particular case, rays will come and converge in this particular point. In the other hand, if we just take a look, until this point there is no change. Here we have the magnetic lens, and the changes is going to happen somewhere in this particular point. So if we just draw that, it will come like this, and the other one it will. So in both the cases, because of this magnetic field, electron beam is converging in a two different plane. So here we are always considering those cases when these rays are coming and merging in one particular point, there is a no energy loss. No energy loss of that electron. So here also same thing, whatever energy loss is happening at the beginning, here also there is no energy loss of the electron. Okay, so here you can see that angle, this angle is very important because this is the angle which is called the beta. And now if you just so here this is the image plane where we can get the actual image. This is the actual image plane. So if we just consider that okay, when some electrons are converged in one particular point, it is up then actual image plane, those rays will come and form a image, and that will give us some kind of blurred images. So the images will be not that perfect, and it is going to affect the contrast as well as the brightness of those images. Now this is all about our chromatic aberration, and if someone is asking, definitely chromatic aberration is also there in electron microscope in a different form. Now we are coming to the another important point that is called that is called the spherical aberration. So now we are talking about the spherical aberration. So what is that spherical aberration? So spherical aberration, we are always considering that okay, there is a glass lens. If you just remember at the beginning, I told that okay, if there is a rays are going through the center of the optical axis, changes will be very less. But whatever electron is going towards the periphery region, so most of the time center of the lens are much more perfect. Okay, and the problem it is coming when it is going towards the periphery of the lens region. So most of the time if rays are coming, those rays will be perfect, and they most of the time they will go and then they will merge properly in one single point. But periphery region of this lens, if you just consider this is the periphery region, which has a different kind of effect if the lens are this curvature of this lens, that one side of the curve and the other side of the curvature is not same, or there is some defect in this particular region. So that will be the maximum at the edge of that lens. So same problem it is there when we are talking about the electron microscope or electromagnetic lenses. So here if we just consider that okay, there is a electromagnetic lens and how there's electron beams are coming, let me draw that diagram and then explain it. So we'll take it first. Any ray diagram, whenever we want to do it, it will be better to draw the optical axis first. If we have a correct optical axis, it will be much more easier. Then definitely the next part we should draw the lens that okay, if there is a lens system and then the image plane and the sample. So if we fix those things, because if they are parallel to each other, the ray diagram will be much easier to draw. So here we are considering this is my sample point. So my sample is somewhere here. So my sample is somewhere here. Okay. So now we have to draw this ray diagram. So first thing first, we have to draw this one. This one will be always like that, very straightforward, that two rays are coming from our sample. And now when the sample it is coming, now this is our lens system. Now in this particular lens, it is, as I mentioned, that there are most of the time the periphery region of the lens, because electromagnetic lens, if you just remember what we draw previously, this is the cross section of that lens, right? So those are the copper wire and it will be connected like this. So maybe you can consider that okay, this is the electromagnetic lens. At the center there will be a hole where rays will go in and it will come out like that. Now we just did a cross section here and this is the part you can see it. This is the part you can see it where rays are going through this. So when there is a one ray is going through the center of this electromagnetic lens, there will be not too much deviation. So whatever rays is close to this optical axis, they will face similar kind of magnetic field. But if rays are, so if this is the optical axis, when the rays will deviate and go towards the edge of the lens. So here also, so here this is the optical axis, and whatever electron will go towards the edge, they will face some kind of different kind of magnetic field if magnets are not perfect. Okay, and that is called the spherical aberration. This is a on axis aberration. So most of the time if the center rays are going through that, they will not face that kind of problem, but whatever rays are going towards the edge, they will deviate in a different way if magnetic lens are not perfect. Now I am just going to draw this one using a ray diagram. So if I just draw a ray diagram, you can see it here. What will happen, whatever rays is at the edge, they will come and merge somewhere here, because due to some kind of aberration, they are feeling most stronger magnetic field in this particular region and they converged in a different position. And the other rays, if we just consider that, okay, let me draw that thing using a blue line. So there are many rays are coming at the center, right? So some are like this kind of rays, this kind of rays. There are many rays are like that. Now these blue rays is coming and converging a particular point. This blue ray, it is converging in this particular point. So if we just continue draw this one, what will get it? It will go all over like this. Okay. Now we'll just use a different color here. So for this one will be much more closer to that axis and it will go and converge somewhere here. So you can see this red rays which is close to the optical axis, they are merging somewhere very close to the image plane, and that is basically not affected that much due to this spherical aberration. Now if I draw this one also, this will also come and merge some point here. So in your red line you can see they are very close to optical axis and they are converging somewhere here. But if you just look at this black rays which is close to that magnetic field and they are deviating in a different way. So these black rays are merging somewhere where the blue is converged somewhere here and the red is converged somewhere here. So in this particular case, this is, you can consider that, you know, the when rays are close to or periphery of that electromagnet, they have a severe effect, and whatever rays is far away from that periphery of the lens, they have a less effect and they are almost going and merging in a plane. Now all these rays together, when they are going to give us an image, that image will be a it will not form a single point anymore. It will form some kind of disc, and it will be a mixture of all these different rays. Initially we are thinking that when these rays are coming and they all are merged in one particular point, so if we are starting from a point, we are expecting a point here. But in this particular case, definitely this black rays is forming a point somewhere here, where the blue rays is forming a point somewhere here, where is the red ray is forming a point somewhere here. Now if we just draw a imaginary plane here, what will get it? Will get some kind of disc diameter, right? So it will be not a single point anymore, it will be some kind of diameter. So when we are trying to image a point, we will not get a point anymore, we will get some kind of disc. So that is because of the spherical aberration of the lens. How do we determine the spherical aberration? Generally spherical aberration is denoted by CS. Now here one more important part is that it will be better to mention that one, that okay, so there will be a magnetic field, how it is affecting when there is a no change. If the magnetic field is coming, how this magnetic field is affecting a rays. So in this case we can tell this is that when CS is 0, but actual scenario is this one, that magnetic field is coming like this. So again, if I just want to draw, this is our theoretical expectation, but actual magnetic field is going like this. So you can see there is a difference between the actual and the theoretical spherical aberration. So pink color, where the spherical aberration is 0, but this blue there is spherical aberration and that is non-zero. So most of the lens system, that spherical aberration, so here that you can see that magnetic field is uniformly distributed, but actual case it is not uniformly distributed, and it is going to affect how electron beam is going to converge and at what particular point it is going to give us an image. So this is the spherical aberration and this is the on axis aberration. Now the next part it is coming, that astigmatism, that we are discussed couple of time, that all the lens system has a 4 component. The first component is deflector, then electromagnetic lens, then we have stigmator, and then we have aperture. So stigmator is connected with astigmatism. The astigmatism is another problem if lens is not very symmetric or not very uniform, or their magnetic field, or when there is a current flow is there, is that current flow is not very uniform. That is going to affect the electron beam. And whenever we are talking about we want to image a dot, if we just consider that there is a dot, I want to image a dot. So lot of time, most of the time we cannot get a dot. So what we can get? We can get a circle. So now, by hand it is bit difficult to draw a perfect circle like this. So when we have an image, if it is forming a perfect circle, still it is okay. Okay, so there is some aberration, but it is forming a perfect disc kind of thing, and it is a circular disc. But in astigmatism, it is a off axis aberration, not the on axis aberration. It is a off axis aberration, and this circle, whatever I am trying to say, the disc or circle, it will be not circle anymore, it will be elliptical in any particular direction. This beam diameter, whenever you will try to measure the beam diameter, so here you are having a point source, but actually you are getting a circle, means you are getting a disc, and this is called the beam diameter. So but it is a circular. But when you have a elliptical beam, if the beam is elliptical somehow, so it is very difficult to measure the beam diameter, because here the diameter will be different, here the diameter will be different. So in case of astigmatism, most of the time we will get an elliptical beam. Okay, let me describe that how we can get an elliptical beam. Okay, so now we are going to discuss about the astigmatism, right? What is this astigmatism? As I mentioned, it will be a off axis aberration. Let us draw the optical axis first. As we mentioned that it will be always better to draw the optical axis. So we have this optical axis, and then we have that image. Now if we just consider that rays are coming, and if this is our lens system, okay, so in this lens system somehow the actual rays are going, so there will be a center point, that rays will go through the center and it will form an image, and that we are going to draw here. So it is going through the center. So now you can see any particular image. Previously when you are drawing, we are trying to keep these things in the center, but here there is some kind of deviation, and that is where we are going to point, right? So there will be a next one. So if there is some kind of changes at the beginning, so that changes it is going to reflect here, and this is the ray, it is merging. So definitely it will go and converge one particular point, where these rays will go and converge one particular point here. So this is one part, but there will be a other rays, it will come and merge somewhere here, and finally they will converge somewhere this particular point. Now if you just continue these rays, what you will get it, so these rays will go like this, and this ray will go like this. On the other hand, due to this different types of magnetic field in one direction, other direction we have a different magnetic field, rays will go like that. Now in this particular image you can see it, so the entire rays is focusing and it is shifted from the actual axis. So if this is the actual optical axis, so it is shifted from the actual optical axis, and then there is a one crossover point it is forming. I am just putting this blue, and the other crossover point I am putting it here. So then you can see there is a two different kind of crossover point. We can get it here, one. So because of this blue we can get a one crossover point, and then because of the red we can get another crossover point, and then merging these two together. So when we are getting an image, we will get we have to converge both the rays together, and then we will get an image. So here you can see there is one rays is going like that, and here, so when it is going to form an image, we will get an image something like that. So the image is what we are talking about when rays are going through the center. If there is a point, rays are going through the center and they are converged in one particular point, and it will give us a point. So starting from the point source, but if we don't, due to aberration, spherical aberration, we are talking about that, okay, there will be some rays will converge like that, and then but all are going through the optical axis, and it will give us a disk like that. And if we look at that disk, so point become a very nice circle. But in this particular case, whatever I mentioned here, due to this different types of magnetic field, in one maybe it is different magnetic field, here it will be multiple magnetic field. So strength is different, and it is converging rays in a different way, and also it is not the axis, it is shifted from the axis, and then we'll get a spherical power spectrum. So our power spectrum will look like elliptical. So this is called astigmatism. If we just consider this is our power spectrum, this is our power spectrum, so it will be elliptical power spectrum. This is called astigmatism, and this astigmatism we should correct using our stigmator. So that I already discussed that stigmator we have to use and correct that one. So I'll just show you one that how that beam should look like before the astigmatism and after the astigmatism. So if we come here, and then we'll discuss about rest of the aberration. So here I just want to show you one thing, that okay, this is our viewing screen. At this moment don't pay attention to this one, we'll come back and discuss about this one, because this thing is connected with our alignment thing as well as the coma. There is another aberration that is called coma. When we will discuss about the coma, that time we will discuss about this one. But actual scenario, you have a circular screen or viewing screen in the microscope room, and if you look at that, there will be a center point where there is a cross mark, and there will be couple of circle, and this white is your electron beam. So you can see if all the alignments are correct, you can see a circular ring, and your optical axis will be here. So that is basically we are expecting, as well as if we look at the diffraction pattern or the power spectrum of that, here you can see what I was trying to say. This is a power spectrum of any EM images. So you can see a very nice circular ring here, and then these are some white rings, white and black rings are there. So this is, so there is no astigmatism in this particular direction, it is a perfect power spectrum. So this is called perfect power spectrum. Okay. Now if I just show you the other power spectrum, then you can see previous one you saw it is a completely a circular power spectrum. There is no no changes, there is no elliptical shape of this power spectrum. But sometime if you look at the diffraction pattern or the power spectrum, you can see there is a change of their shape. It is looking like a elliptical shape. This is not a circle anymore. So this has some astigmatism in x-axis, and here you can see there is some astigmatism in the y direction. Sometime you can see there is a elliptical shape of the power spectrum in the this diagonally also. So this is called astigmatism. This is the when lenses and magnetic fields are not symmetric, and we will get this kind of power spectrum, and that we can correct using the stigmator. So we'll stop it here today, and the next class I am going to discuss more about the other aberration, mainly coma and coma free alignment, as well as the different type of distortion. Thank you all.